The word stable comes from the fact that if we sum a number of random variables that have a given stable distribution, their sum also has the same distribution, which is true for Gaussian variables. So the Gaussian distribution is one stable distribution, a friendly one. It's a generalization of this property. In particular, it's closed by aggregation. If I aggregate a number of random variables that have stable distribution, then they have also stable distribution. Which is not surprising for a limit, right? If we take the closure of something, then usually it's stable by the operator that led to the closure. So here the operation is aggregation. For example, if I aggregate n random variables, depending on what we can say about the random variables, what can we say about the aggregation? So x bar is 1 over n, the sum of the x. When n is large, what can we say about the aggregation? So if xi is heavy-tailed with index p, then x bar is approximately a stable distribution with index p. Yes, so this is true, and this is the central limit theorem for heavy-tailed distribution. That says essentially that if we are heavy-tailed with index p, then the heavy-tailed is conserved at the limit because the stable distribution with parameter p is heavy-tailed. But the distribution may be lost here. In particular, if xi is Pareto with index p, and if p is less than 2, then we're in the case here, then the limit is not Pareto, but is stable, which is what we had seen in the previous diagram. We saw that when we aggregated here we have Pareto, a straight line everywhere. When we aggregate, here we have a heavy tail, but not Pareto. It's not a straight line all along the diagram here. So this is a sample of something that is an approximation of a stable distribution. So B is wrong, is always wrong. C, if xi is Pareto with index p, then is it heavy tail? Yes, it's true only if p is less than 2. So C is true if p is less than 2. So in general, it's wrong. It's not always true, at least. So the correct answer is D. Here. So a variant of this, yet another quiz. I aggregate now, or I sum, or I take the average of n random variables. N is not necessarily large. What can we say? And the correct answer is both A and B, which is the majority. This is what we just saw, I just said a minute ago. If it's a distribution is stable, then we aggregate independent replicas of this. We have the same distribution here. In fact, it's stable with index p. In fact, it's exactly the same distribution. And this we know also from the Gaussian distribution. An aggregate of n independent random variables that are Gaussian is also Gaussian. So this is true for both here. Why do we care? Well, we care, for example, when we use the central limit theorem for computing confidence interval for the mean here. Assume, for example, that I have n random variables that are drawn from something that is heavy-tailed, for example, Pareto with 1.25, p equal 1.25 here, means this value for the PDF. The true mean can be computed either by integrating this, or you look up Wikipedia or something else. You find that the true mean is 5, and the median is 1.74 here. Now assume I don't know this model, I have given only the data, and I want to estimate the mean and the median here. Right? How would you do it? Both are correct formulas. They are the textbook formulas for computing a confidence interval for the mean and for the median here. But we should look at the conditions under which they make sense. B always makes sense. When we do things based on order statistic, it's robust. So this is true as long as it's IID, whatever the distribution here. So B is correct. But A is true if the central limit theorem holds, which implicitly assumes that the variance is finite, which shows up in the formula, because in the formula we compute this, which is an estimate of the variance. The true estimate of this is plus infinity. And of course, you have a finite data sample. You will not find plus infinity. You will find a value. You're trying to estimate something that is infinite, so you will find some more or less random number that will tend to be large if your data sample is large. A larger data sample is likely to give you a larger value of S, and then probably this thing here will give a weird result here. And the weird result comes from the fact that this was assuming that the distribution is Gaussian of the aggregation, of the averaging that we're doing, which is not true if we have Pareto 1.5 here. So this is visible in numerically also. So this is what I said. We saw this example already, but now we can understand it better. I compute a confidence interval based on so I did it for this data set drawn from this distribution. We see it's not Gaussian, but it's worse than non-Gaussian. It's also non-Gaussian after aggregation, which I can test here by doing bootstrap estimates of the mean. Here I'm trying to see whether the central limit theorem works. So one poor man's approach is to use the bootstrap. The bootstrap is what you can do when you don't want to do anything else. What I did is I did a large number of simulations of this by resampling from this. So I put all of this in a bag. I draw 100 times with replacement from this. I compute the standard mean, so the mu bar, and I do that a very large number of times. If the central limit theorem holds, this should be approximately Gaussian. At least if the bootstrap works, because what I'm doing is I'm approximating the distribution of the standard of the sample mean. So this is what I did here. By bootstrap I obtained this, and does it look Gaussian? Well, not really here. There is a probably systematic deviation here. The number of samples is small. If I do it with a larger number of samples, then we see then clearly there is something different here. It's not a Gaussian distribution here. So the central limit theorem probably does not hold here. Then I plotted what is the confidence interval I obtain, and the true mean is here. We see that when n is small, then it's grossly wrong. When n is very large, it is wrong also, not as grossly, but it is wrong as well. The true mean shows some n is very large here, so we would expect a better fit if things would be okay. Contrast with the median, right? With the median, the true median is always exactly in the confidence interval. When the number of samples is very large, the confidence interval is very small. This is what we should expect also for the mean if we would be in the domain of application of the central limit theorem. That's the bad news, and that's why we go through this, is that there are cases, those cases are not completely far-fetched things, where the central limit theorem does not work. It doesn't work when you have distributions like this. So what is happening here? You have a distribution that most of the time has values that are very small here, between 0 and 100 perhaps, and once in a while you have a value of a few thousand here. If it's an outlier, okay, that's a measurement mistake, you remove it. But if it's things related to the popularity, I mean, this is how many times this file was downloaded, it might not be an outlier. It might be that your distribution really has a few big hitters that have large values, and the mass of YouTube files are causing a usage of resources that's very small. So if you have such things, okay, thank you. I'll do without it. So it's important to realize, well, as long as it lives, let me try. It's important to realize whether it works or not. So one way is to, poor man's approach to the bootstrap with, if you have a doubt, to look at whether the Gaussian distribution seems to hold. Another way is to look at your distribution. If you have a huge number of data points, usually you can see that only if you have a very large number of data points, because you need to plot here in log-log scale. That means there's a huge number. There are millions of data points here. Otherwise, your log-log scale will be very short here. So you have millions of data points, and you find something like this, then it's a power law. You can estimate the slope here. And if your slope P is less than 2, then bingo, you have heavy tails, so you're stuck, or you have found something that, for which you will need a special treatment here. Which means you can concentrate on the very large values, or at least, or use median rather than mean, for example. Voilà, that's what we will see about the stable distribution and the heavy tail distribution. We will conclude by seeing how in practice we can fit distributions when we have those embarrassing tails that are power laws, for example. The classical approach is to use combination and also to handle what is called censoring here. What is censoring? Well, assume you want to fit something, for example, the distribution of the amount of work done by a server. Then you know that some of the jobs will have very large size, but not many. So you can think of a log-normal distribution, for example. So the problem becomes, I want to fit a log-normal distribution. Why log-normal? Well, because it's easier to fit than Pareto. Pareto is also easy to fit, but easier than stable, for example. Because if I take the log of the data, I have Gaussian here. So it's very easy to do. However, there is a small problem here, that when we fit a log-normal distribution, perhaps it is because we want to fit well the tail, the very large values. But we will not see many large values. In fact, we will see, if we have a data set of even millions, we'll see a few large values, but a log-normal distribution has a tail that goes to infinity. So by nature, if we're interested in fitting something where an important modeling artifact is in the tail, we have to capture the fact that we can, by nature, see only part of the tail. When we fit an exponential or a Gaussian distribution, we don't care about this because most of the data is concentrated close to the mean for the standard, a bit further from the mean for exponential, but not as far as for heavy tail distribution or fat tail distribution like the log normal. So in order to do the things, to avoid possible artifacts that I will illustrate in a second, the idea, as usual, is to pose the right statistical model or the right probabilistic model of what we do. So we want to fit data that comes from some distribution, let's say F0, but in reality, what we observe is a truncated distribution. We observe an experiment where we draw a sample from this distribution, and we see it only if it's larger than some threshold A. Because our experiment is finite, for example, we don't do things forever, or because we can measure on the things that are below some size. If that happens, this is called censoring. We're trying to estimate the parameters of a distribution that we have observed conditional to be smaller than something. So the first step is to realize that we're in this framework. The second step is to handle it. How can we estimate this given that, right? Well, in order to do that, we need to map this to PDF because we will do maximum likelihood. So if I do this experiment here, I have a distribution with PDF F0, little f0, CDF capital F0, that is censored to a value A. What I observe is the censored value. What can we say about the PDF of what is observed? And the Dirac on A, which is the correct answer, you have perhaps recognized here something that we have seen in the simulation chapter, which is called rejection sampling. We do generate from some distribution, test whether something is true, and return accept the output only if the condition is true. It's called rejection sampling. What does rejection sampling produce? It produces an output that has a distribution equal to the conditional distribution of x given the condition here. So it's the conditional distribution of x given that x is less than a, which is equal to this. That's the probability that x is less than little x given that x is less than a, then the probability of the 2, which is given by this, divided by the probability that x is less than a. So it is the ratio of f divided by the CDF. In the hazard rate, we had the PDF divided by 1 minus the CDF. Here in censored data, truncated data, we have this here, which is essentially the CDF, the PDF, multiplied by a constant. So that is correct. So when we observe that, we don't change the PDF other than renormalizing, of course, because we have a smaller set of values here. How can we estimate it? Well, the textbook's method says log likelihood. So I have observed some data xi. I want to estimate the parameters of my model. The parameters are two things: the unknown distribution f0 and the model and the threshold a, right? So, and the PDF will be that here, right? So what is the log likelihood? Well, I take the log of this. It is the product of this. All the data points are independent, so that gives a sum for the log. So it gives me this expression here that has a term that depends on x and a one that depends only on the number of data points and a, right? So the problem is to find the parameter theta. I assume my distribution f of 0 depends on a parameter theta that maximizes this. And of course, we have this constraint here, right? X has to be less than a, which means that a has to be larger than all the x here. Right? Now, if you try to maximize this, you have to choose two parameters, a and theta. Then with a bit of work, we can see that the solution is to take the smallest value of a that satisfies the constraint, which is the max of all the values that I've seen. And then, given this value, I need to maximize that, which means fitting the data to the distribution with parameter theta, where the threshold a has been given here. So how do we do that? Well, it depends on the distribution that we have. If the distribution has few parameters, it's an optimization problem with few variables, so we can ask any brute force optimizer like fmin search to do it. Here I did it for a data set that is an artificial data set obtained by sampling a log normal distribution with those parameters truncated to 20,000. So I stop at 20,000 from a log normal distribution. And for some reason, I assume the shape parameter, mu here, sigma here, is the one that I'm interested in here. This is the red, which is not visible, is below the blue, is the fit I obtain if I do this censoring approach. So first I estimate A, then I do the fit given A by maximizing the formula that is given here, right? So if we look at what we're doing once we have A, it's like adding a penalty term to the log likelihood. Right? We find the theta that maximizes. This is what we do if we ignore the censoring. I give you the 10,000 data points. They're all between 20,000 because my measurement never produces anything larger. But I ignore the fact that they're forced to be below 20,000. Then what I will maximize is this, the sum of this here. Now if I know A, which I've estimated by this method, I know I have to find a penalty term. I need to add a penalty term for every theta, that is this term here. So that will produce a different fit. At least if the distribution puts a lot of weight on the tail. If it would be a Gaussian distribution, probably not, but if the distribution puts a lot of weight on the tail, it will make a difference. And here the difference is visible in those two scales here. The dotted line is the log normal distribution I would fit if I ignore this penalty term. So if I ignore the censor, I obtain a significantly different distribution here. Which makes sense. A log normal distribution will try to say, I have a log normal distribution that has no value larger than 20,000. And the only way it's possible to have this is to have a log normal distribution that's very close to a Gaussian distribution that has a very small tail. And the fit would be very bad because the data are the blue here, right? So the true one is the blue here. So the fit would be very wrong here. Even in log scale, if I do log scale, I would see perhaps less large, but still a visible difference between the two. So take-home message, if you do care about heavy tail or fat tail and you fit something to take into account the tail and your data is truncated, then you should somehow account for it. And it's very easy to do. It just amounts to adding a penalty term that can easily be applied. But very often we want to do something, go one step further, not just truncate, but for example, here is a data sample I have. This is taken from papers of file distributions. And this is what I see. So this is very likely the kind of things I will see when I aggregate or average a large number of things that are heavy-tailed. So the distribution of objects, of loads due to YouTube files, for example, I will see something like this. Now, this is probably a stable distribution, but I don't want to be bothered by the stable distribution. So frequent procedure consists in saying, let me separate the tail from the body of the distribution. So I will fit some distribution here, normal or log normal here, and here something that is a power law. So I will fit Pareto here, which means this PDF here. I will say, I will fit a weighted sum of a truncated distribution from some distribution F1 at a threshold A here, and another distribution that is truncated, but from the left, a distribution F2 here. So this is what I do. I need to put the weight here because I want the sum of this, the integral of this, to be 1. So if I take only this is a PDF. This is another PDF. I need to do a weighted sum with sum of the weights equal to 1 to be a PDF here. So this PDF, can we interpret it as a simulator output? I propose here 2 simulation programs. Does any of the 2 produce what we're interested in? The majority says both, which is correct. In fact, both programs are producing a valid sample. Why? Well, first we draw a random number between 0 and 1, and we test whether u is less than q or larger than q, which means we're drawing a binary random variable. With probability q, we do this. With probability 1 minus q, we do that, which corresponds to the first and the second term here. And we draw an x from f1 until x less than a, so this is an entire loop here. And this is rejection sampling, so it produces a sample of this. This also produces a sample of that. Of course, the x that is here in the loop is a local variable. And you will draw, so depending on the value of u, you will deliver one of the 2. So this is exactly producing this. This is correct. B is also doing the same thing, but B is first drawing x and y and decides which one to draw, to deliver, depending on the choice here. So it produces also an output that has the same distribution. Which one is more efficient? A. Why?
So we have here doing both equations.
Yes, so B draws 2 random variables, so it calls the random number generator twice. Here it draws it only once. So it's more efficient. Both were, but A will be faster. If you need to do it 1 million times, it's better to do A. So we know completely how to interpret it, and now how to fit it, then we have to compute the maximum, the log likelihood, but we know the likelihood here. So for each of the points, for each of the data points, we have to compute the value of this. And now the parameters are A, Q, and the parameters of F1 and F2, if there are any parameters. Typically there are. So we need to estimate A, Q, and then the two parameters here. Once we have estimated A and Q, or at least A, yes, A and Q, then it's the two problems are the two functions will appear separately. By doing the same kind of manipulation that I will skip, it's possible to simplify a bit the problem by observing that if we know A, the breakpoint, the point where it breaks here it's not very clear where it breaks, right? I see there is a straight line, but does the straight line start here or there? Then it's not very clear. But if I know the breakpoint A, then the maximum likelihood estimator of Q is simply the proportion of points here. Once I have obtained this here, if I have 10,000 points to the left out of 20,000, then Q is 0.5, my maximum likelihood estimate. So that is always true and easy to find out. So the only problem is to find A, and once I have A, then fitting the two is fairly easy because we have two different bags of data points with a penalty term. So that can be done fairly easily. Now, how to find A? Well, we have seen one method for that is to compute what is called the profile log likelihood. What is the profile log likelihood?
So different A values we calculate the likelihood and what the score.
We calculate the likelihood, we calculate the score. So the score is the sum of the log of those likelihoods, or the product of those here. Instantiate it at all the points here. And optimized over Q. So optimizing over Q, it's easy to do. So optimizing over the parameters of F1 and F2. So I solve the optimization problems, assuming A is given. So I fix A to some value, and I do the fitting. This is what I did here, but what you need to do is not just the fitting, but compute the log likelihood. We've done that in other contexts already. We've seen that if things are Gaussian or Pareto, it will be easy. Then it's easy to have closed form for the log likelihood. And then I plotted it, and the maximum log likelihood says the points that gives the maximum is the one that is my estimate of A. Now here you see you don't have such a beautiful shape here, but that's very typical when you start having heavy tails like you have here. So, but it gives an idea. First, it gives some uncertainty. We see that the breakpoint A is in the region, and where exactly in the region is probably not easy to find, but it's around those values here. So I fitted the one that has the largest value, this one, that gave me this point here. Voila. This is how, I would say, we handle the presence of very large tails concretely, and all the technical problems that have to be done. Voila. I think we will close here for today. In exercise series of this, you will have the opportunity to exercise your skills in estimating things with heavy tail and other joys of the same kind. Tomorrow we will start PALM calculus, and we will also see the results of the forecasting contest.